Ladies and gentlemen, welcome to lecture number 6, where we'll be looking at digital modulation schemes. This is in a course EEE 4682, telecommunication or communication systems. The presentation outline will look as follows. I'll briefly talk about the introduction to digital modulation schemes, then we'll look into details, amplitude shift keying, frequency shift keying, phase shift keying. We'll look at other modulating schemes. Then we'll look at the pulse code modulation schemes before I give you a tutorial. Now, the process of changing one of the characteristics of an analog signal, typically a sine wave, based on the information in the digital signal, is basically classified under digital modulation schemes. Basically, under this, what you have is that you'll have the information or message signal in digital format, but then you have the carrier, which is analog, and then you begin to vary any of the characteristics of the carrier signal, be it amplitude, the frequency, or shift, in accordance with the digital data that you are intending to transmit. And to achieve this, there are three popular methods, which are basically digital modulating schemes. And these are amplitude shift keying, frequency shift keying, phase shift keying, but I also talk about pulse code modulation in this presentation. Now, in digital modulation, like I said, the information or message signal will be in digital format, and this can be information coming from a computer. Then you pass it through the modulator where you add the carrier, and then the characteristics of this carrier will be varied in accordance with the format of the digital information, in which case the zero would either represent a change in the amplitude, or a change in the frequency, or a change in the phase of the carrier signal. So let's talk about amplitude shift keying. This is one old digital modulating scheme that we should consider. And in amplitude shift keying, basically the two binary values are represented by different amplitudes of carrier frequency, whereby you will have binary 1 representing, say, a no change in frequency, while binary 0 will represent a change or amplitude of the carrier. Yeah, so in this case, we have, if you look at this diagram, you will notice that in amplitude shift keying, you have a binary 1 here, basically representing a no change in terms of the amplitude of the carrier. The amplitude of the carrier here remaining the same, while a binary 0, which is basically denoted in this format here, means that your amplitude here will change wherever there's a 0. The amplitude is changing. Equally here, the amplitude of the carrier signal will be changing, but wherever you have a 1, it means the amplitude of the carrier remains as is produced from the carrier generator. The major disadvantage of amplitude shift keying is that it's very prone to noise, therefore it's an efficient modulating techniques, and you can only use it up to 1,200 beats per second on voice correct lines. It's quite applicable in optical fiber as one of the modulating schemes that you can employ there. But except for the noise issues, this method is very used. To shift keying in terms of a diagram, you will notice that, like I showed previously, you have a carrier signal here, which is analog in nature. Then you have a digital signal here, this digital signal will vary the amplitude of the carrier in accordance with the format of the digital signal, whereby in an event you have the digital signal being equal to 1, the amplitude of the carrier remains the same, but in an event you have 0, the amplitude changes. In this case, it is changing to 0. And if you look at the diagram on the right, you have the digital data message signal being mixed in the modulator from the carrier, which is basically analog in format, and the output will look as the signal shown here. So basically in amplitude shift keying, what you're changing or varying is the amplitude of the carrier, but you keep the phase, you keep the frequency of the carrier constant. Now, in terms of advantages and disadvantages and the application, the major advantage of amplitude shift keying is its simplicity, but as a major disadvantage is that it's prone to noise and interference. Usually, whenever there's a change or in value of the amplitude, it makes the system to be prone to noise. You can, however, apply amplitude shift keying to transmit digital data over optical fiber. It's quite useful in that area. Next, I want us to talk about the frequency shift keying. Under frequency shift keying, basically what you're doing is to keep the amplitude and the phase of the signal, but you'll be varying the frequencies. Therefore, in a practical system, you will have 2 carrier signals denoted by F1 and F2, and they will be in such a way that whenever you have a binary input of 0, then the signal will take the frequency of F2. Whenever you have a binary input of 1, it will take the frequency of the first carrier signal F1. And so if you look at this diagram here, basically what you are seeing here is a scenario where F2 here denoting the frequency of the second carrier, and where you have a binary input of 0, F1 in this case denoting the first carrier signal for a binary input of 1. So wherever you have 1, it will take the frequency of the first carrier, and wherever you have a binary input of 0, it will take the carrier, the frequency of the second carrier. The major advantage of this shift keying is that it's less prone to noise than shift keying. It is used also up to 1,200 voice grid lines. However, I can also use it at higher frequencies, ranging from 3 to 30 megahertz. You can also use it in higher frequency on LANs using coaxial cables as well in terms of its application. Yeah, so in terms of the waveforms, you notice that the first waveform represents a message signal, which is in binary format consisting of 1s and 0s, and you have 2 carrier signals there, VC1 being of lower frequency and VC2 of higher frequency. And whenever you have an input of 1, it will carry the frequency of the first carrier signal. And whenever you have a binary input of 0, it carries basically the frequency of the second carrier. Then in terms of advantages and disadvantages, FSK is less susceptible to noise, like I said, but the major disadvantage, it requires a wider spectrum, which is almost twice that of ASK, but you can apply it, over voice lines in high frequency radio transmission and so on. The next we'll talk about the phase shift keying. Here you are keeping the amplitude and the frequency constant, but you'll be varying the phase. And the popular one you have under phase shift keying is what is known as the binary phase shift keying, where you have a binary 1 to represent a certain phase and binary 0 to represent a second phase. So for a binary for a binary input of 0, 0, you get, you know, the phase shift represented by 180 degrees or pi. For binary 1, you get a second phase of 0, which is an angle of 0 for input of binary 1. And again, whenever you have a binary input of 0, it will take the second angle, which is 1/8 or pi radians. So that's basically on the binary phase shift key. In terms of diagram, you notice here you only have one carrier here. The only thing is that whenever you have an input of 1, it will carry the phase, you know, the phase of pi, and whenever you have a binary input of 0, it will carry the phase of 0. And then in terms of the diagram, it's shown on the right. Basically, the signal, the phase shift key output signal will be changing in terms of angles of phase in accordance with the message signal, whether it's a binary, it has a binary input of 1 or a binary input of 0. The major advantage of phase shift keying is that it's also less prone to noise. Since the amplitude is kept constant, it's more, it makes efficient use of bandwidth is unlike FSK, whose bandwidth was twice that of ASK, but it has one major disadvantage. It's more complex in terms of signal detection and recovery process than ASK and FSK. So this is a summary of the 3 modulating schemes. In the first one, you're changing the amplitude. In the second one, the frequency is changing, or in the third one, the phase or angles are changing in accordance with binary input of the message signal. There are other digital modulating schemes such as quadrature phase shift keying, quadrature amplitude modulation, and so on and so forth. And I leave this for you to do as an assignment to explore other digital modulation schemes. But before we wind up on this lecture, I want us to talk about pulse code modulation, which is another digital modulation schemes using a pulse. But in this case, this is usually just a digital analog digital conversion process where you sample a signal, or you pass a signal into a low pass filter, then it's sampled and quantized, and then you have a PCM output, which is basically a digital signal. The diagram here shows a sine wave which is to be sampled, usually at twice highest frequency. Whatever is the frequency of that, you sample twice that much, and then the signal goes through the process of quantization and decoding until you achieve a PCM output as shown in the waveform below. The advantage of PCM is that it's robust to noise and interference. It's more efficient in terms of regeneration of the signal. It has an efficient signal-noise ratio and bandwidth trade-offs. It also has a uniform format. It's easy to add and drop the signal, and it's even more secure. And related to PCM is what is known as a digital signal number 0, DSO, or DS0, a digital signal rate of 64 kilobits per second. And how that is carried out, if you are sampling at twice the highest frequency for audio, for example, usually audio will have a range of 20 to about 3.6, which is rounded to 4 kilohertz. So if you sample, at twice that frequency, which is 4 times 2, you get 8 kilohertz, which is basically number of samples per second, and each sample will have 8 bits. You have 8 bits per sample, and multiplying those two gives you basically the data rate of 64 kilobits per second. And that's the basic digital signal 0. But we also have digital signal 1, DSL or DS1, also known as T1. It's a T carrier signal schema devised by Bell Labs in America. DS1 is widely used standard in telecommunication in North America and Japan. But in Europe, there's an equivalent of E1, which is used in place of T1. Technically, DC1 is a transmission protocol by a physical T1 line. However, the terms DC1 and T1 are usually used interchangeably. So let's talk about DC1 circuit. Usually this circuit is made out of 24 DS zeros. So if you multiply, since one DS0 is 64 kilobits per second, multiply that by 24, you're going to get 1.544 megabits per second for DS1. And if you take the European equivalent, which is an E1, which is made out of 32 DS zeros, the line data rate will therefore be 32 by 64 kilobits, giving you 2.048 megabits per second. So that becomes really the data line for an E1, data rate for an E1. What is important to notice here is that each DS0 represents a subscriber. So in an E1, you have 32 subscribers that are possible, whereas in a DC1, you have up to 24 subscribers that can be accommodated, where for audio and in PSTN network, this would represent one subscriber or one subscriber owning a handset. And these are some of the basic references that I've used and some tutorial for you to take. I'm particularly interested in the tutorial D in this question, where you have a PCM audio signal range from 20 to 4 kilohertz, assuming an Nyquist sampling being adopted. And if there are 8 bits per sample, let's calculate the sampling frequency and let's calculate the data rate. In terms of, just to give a hint there, we are told the range is 20 hertz to 4 kilohertz, and we normally sample twice the highest frequency. Therefore, the sampling frequency is expected to be 2 times 4, giving about 8 kilohertz. In terms of the data rate is basically sampling frequency times bits per sample, and that gives you 64 kilobits per second.